I think you can all hear me pretty well because I can hear myself really well. My name is Lalitra. I'm a program manager on the Windows Fundamentals team. And I work on performance tools, specifically the Windows Performance Toolkit. And this past release, I've been particularly focused on how you can use these performance tools to improve app performance. Now, in this talk, what I'm going to talk about will be the mental model for interacting with the platform. So the mental model for interacting with the platform really is about how's your app working with the platform? What do you need to know in order to understand the performance impacts of your app working with the platform? And we'll be talking about this for the two terms you've probably heard a lot of, fast, fluid. What sort of scenarios do we mean when we talk about both the fast pillar for performance and the fluid pillar for performance? And what does that interaction with the platform mean for fast and fluid? And then we'll briefly touch on a high-level analysis approach that you can adopt to put these ideas that we're going to develop over the next hour into practice. Now, how many of you already have apps in the store, in the Windows Store? All right, seeing a fair number of hands. I'm hoping the rest of you are working on apps right now, about to go to the store. But in either case, especially as you guys have some cool devices in your hand, you probably used store apps, you know? And you've probably seen friends and family use store apps on various devices. And you know, just as your experience and their experience is significantly affected by the performance of these apps. That's going to affect the satisfaction with the device that you guys purchase. And so we want to make sure that you guys have everything you need in order to make apps faster, more fluid, better. Our approach to improving performance at Microsoft follows this performance journey. And if you were at some of the other app performance talks, you might have seen this slide, where you're talking about designing and planning, architecting your apps and whatnot. In this talk and the next talk, we're really going to be focused towards the test and measure and analyze portions of this journey. And our approach here is going to be, in this talk, we're going to develop that fundamental insight to deliver on fast and fluid. And in the next talk, Shel Steryoff, my peer, who's sitting in the back, will be talking about how to use the tools, the Windows Performance Toolkit. And the tools are really how you're going to see the complexities of your app's interaction with the platform, because it is, of course, a highly optimized, powerful platform. And so the ideas that we're going to talk about and develop now are going to help you understand what's going on, and the tools will help you see exactly what's going on in your given scenario. Let's get started. First, fast. So for fast, we're going to talk about critical path analysis and the UI framework. First, the scenarios we mean when we're talking about fast are scenarios like launch, page navigation, resume, resize, and rotation. Scenarios, any scenario where you want the user to be waiting the minimal amount of time to go from that A to B, to go from the start of their scenario to being done with their scenario. Let's take a look at a quick example here. Here I have a demo app that showcases a couple of different performance issues. Here, when we're talking about things like fast, I can see if I navigate to this first page, there's significant noticeable delay before the page is done loading. Similarly, if I tap on the second page, again, there is significant noticeable delay before the page is done loading. Now, Shel is going to dig into exactly this app, a trace from this device, and see why is this happening. Her approach when she's looking to improve performance is going to be critical path analysis and optimization. Critical path analysis is a high-level workflow where first you're going to identify your critical path. Your critical path is at A to B. In that example I just showed you now, that the A, the start of my scenario, is when I tapped on the page to navigate, and B is when the page is done loading and I can fully interact with it. For launch, that would be when I tap on the live tile, and then when the app is fully launched and my user can use it fully, that's when launch is complete. And so that's my critical path. My critical path is, what is my app doing? What is the path my code is taking to go from the start of my scenario to being done with the scenario? Once we've identified that critical path, we're going to identify each phase on that critical path. And a phase is a chunk of activity. It's that discrete phase of activity that your app is doing. So in launch, for example, it might be, you might have a phase of activity where you're building a view. You might have a phase of activity where you're checking for updates, going to the network, whatever it might be. You want to identify what are the different pieces of work you're doing in this critical path that might be causing you to not meet your goals for a given scenario. Next, you're going to drill down into each phase, see what resources are you using, what resources are you blocked on, are you waiting, or do you have any delays of some sort? And then we start to optimize. Let's take a look at a high-level example. Here I have a critical path for launch. I have a comics app that I want to optimize, and it's taking too long to launch. So I've identified my critical path, and now I'm going to identify the phases of activity. And here I see 4 phases of activity. I'm checking for updates, enumerating comics, building the display, and then decoding images. Now, during this whole time, my user is sitting and waiting, looking at a very pretty splash screen. And we want to make sure that the amount of time they're waiting is as low as possible. So as I drill into it, and I want to optimize this critical path, I'm going to be asking myself a couple of questions for each phase of activity. Can we not do it? Does this phase of activity, is it necessary to provide that great experience to my customer? If not, let's get rid of it. Let's eliminate it. Can you do it earlier? Can you cache? Can you persist some information so you don't have to do that calculation on this critical path now? Can you do it later in parallel? Can you do it more efficiently somehow? And as we ask ourselves these questions, we get to an optimized critical path, where the key thing to note here is that the start and done, the amount of time that my user is waiting, is significantly lower. So how do we get here? We took a couple of different strategies when we were talking about optimizing this critical path for this comics app. First, I'll draw your attention to enumerating comics. If you recall, in our original critical path, we looked at what comics we had during launch, every launch. We don't do that anymore. We got rid of that phase of activity. Instead, we're going to cache and persist some information. We're going to just persist that comic information, then we're going to check for changes, and we're going to do that after launch so that the amount of time our user is waiting is very low. Similarly, checking for updates, we're going to defer that work as well. This used to be in our critical path for launch, but now it is past that. Decoding images, we're doing this in parallel. Building the display, we're doing that faster. We're making it less complex and virtualized. And we'll touch on a few of those points a bit later in the slide. And we can take this approach of critical path analysis and optimization a step further. We can take any of these phases of activity, and we can make that the critical path we're looking at. We can dig in for building a display. What are the discrete sub-phases of activity that we might be doing there? So you can take this workflow, this approach for optimizing your critical path, and use that in a very powerful way to understand what's happening in the system and understand how you can make changes. Now, as you're digging in to the critical path, one of the things that you're going to see, and you might have already seen if you looked at this, is that there's a ton of time, potentially, that's spent in system. You're going to see, hey, I have time spent on my app. I know that's me. And then there's time on the system, and then it's back to my app. And when we see that, what's important to remember is that the system work is happening because your apps are relying on a UI framework. This UI framework, you're relying on this framework to do a bunch of stuff for you. You're relying on it to figure out where things go on the screen, to handle some animations, all sorts of things, right? And so when you see system, the question we're asking ourselves is, what is system? What is this UI framework doing at the request of this app? And to understand what the system, what the UI framework might be doing, here are a couple of key fundamental concepts first. First, UI thread and element tree. So all of these concepts, by the way, apply equally to XAML apps and HTML apps? And actually, I'm kind of curious. How many of you are working on HTML apps? All right, a couple of hands. How about XAML? How many of you are XAML? All right, cool. Okay. Yeah, so for both languages, for both XAML and HTML, this applies equally. So UI thread. The UI thread is your key to responsiveness. Your UI thread is what's executing your app's code. It's responding to some input. It's handling out where things go on the screen, and it's doing a bunch of framework tasks for you. So UI thread is important because whenever your app isn't responsive, you want to understand why that's happening, you look at the UI thread. The element tree is just a data structure. It's where your items in your app are contained. It's an object model. For you HTML guys, this is your DOM. Or if you work with web pages at all, this is your document object model. In XAML, we just call it a visual tree. We'll just call it element tree or object model interchangeably. They mean the same thing here. And an element tree is really a tree structure. You've probably seen this before. On your left here, you can see the body contains a container. Within that, you have the image, list, and the various list items. Now, to go from this tree, which contains your items, to what you see sort of laid out on the screen on your right, where you have everything laid out nicely just the way you want it, there are a bunch of framework tasks that are occurring. These framework tasks are the display pipeline. And the display pipeline is the set of tasks that the UI framework is doing on your app's behalf to get your content to the screen. So let's go through this. First, loading and parsing your element tree or object model. So this makes sense, right? This step is about figuring out what items am I dealing with. And so we might take your HTML file, your XAML file, and parse it to figure out, okay, what are the items that we need to know about, and we'll put them in that tree, in that object model. Similarly, you might have some dynamic changes to your object model. You might be pulling in content from the network and pushing that into your DOM, into your visual tree, whatever it may be, right? So this is the first step. Before anything can make it to the screen, we have to get it into our element tree or object model. Next, now that we know what items we're dealing with, we're going to do formatting. Formatting takes those items and figures out what they look like. So formatting is things like, hey, what font is this block of text? What size is this block of text? Things like that. I might say, hey, I have this block of text. I need it to be 32 points to go UI. That activity is figured out during formatting. Next, layout. Layout is figuring out taking the items that we're dealing with. That's the first step. And we figured out what they look like. That's the second step. Layout is the third step, where we're figuring out where they go on the screen and how much space they take. And so this might mean, hey, that same block of text that I formatted earlier, hey, I want 100 pixels indented from the right and 10 pixels pushed in from the top. We figure that out during layout. And if it needs 600 pixels width to fit, great. We're going to figure all of that out in layout. And you can see the relationship between layout and formatting when you think about, hey, if I'm trying to figure out how much space this is going to take, that's going to be affected by formatting, right? If I have a block of text and it's 32 point, it might require 600 pixels, but if it's 12 point, it might require 300, right? Arbitrarily speaking. And so this is one of the things, there's a relationship between layout and formatting, where before we start to lay something out, we'll look to see, hey, has it been formatted? Is it done? Now that we've finished with that, where we figured out what items we're dealing with, what they look like, and where they go on the screen, next, we're going to display it. Now, to display it, this step is really about taking that work we've done and printing them onto different layers. Now, these layers, if you used Photoshop before, it's a similar concept to layers in Photoshop, where you have, you can independently manipulate a given layer without affecting other stuff. And so we'll print your content onto different layers as needed. And depending on what framework you're working on, that sort of works a bit differently. But at a high level, we're printing them onto different layers. And then finally, we hand those layers off to composition, where they get composed together. So at this point, you can see, when you see all sorts of activity happening in the system, why that might be taking so much time. You're going through a display pipeline, and if your app's UI is very complex, that might mean that your app is having to spend a lot more time in the framework to get its content to the screen. Now, the other reason you might be seeing lots of time spent in system is because your app is invalidating some of the work you've already done. So an invalidation means that some of your content on the screen, it's no longer valid. It's old, it's stale. It needs to be replaced with something new. And these invalidations are caused by input events, manipulations of your object model or element tree. And what it means is that, hey, we have to go through that display pipeline again, or at least portions of it, in order to get your new content to the screen. Right? And does that make sense, you guys? In that, hey, I have content on the screen, something has happened, I've navigated to a new page, I've clicked on a button, something has happened that causes me to have new stuff I need to show on the screen. As such, of course, the old stuff needs to be taken down, but that means that the work we did to get that old stuff on the screen might not be necessary. That's an invalidation. Now, these invalidations can vary in scope. You might have invalidated pretty much the entire page, such as in that page navigation example, where I did some work to get that page first loaded up. Then when I navigate to the next page, that work is invalid. It's no longer relevant. It's time spent doing something that's not needed for this new page, right? Or they can be more contained. Example, I tap on a button and it needs to be highlighted. That's an invalidation. That's very contained, hopefully. Or it might be something like, consider if you have an RSS app or a mail app, and you have a list of items and you have a viewing pane. Whenever you switch between items, you need to show the new content in the viewing pane. You're invalidating the old content. So how do you manage all of that? And because there are costly recalculations, right? You're spending time in the display pipeline again to get new content there. So you want to make sure each invalidation is necessary. You're mindful of your invalidations if you're seeing a lot of time in system. Let's take a look at some scoped examples of different types of invalidations. So here we can see on your top left here a format invalidation. This would be something like a font change. I've bolded the text in this first list item. That means I had to redo the work for that list item to get that content to the screen. Next, on your top right there, you see a layout invalidation. And here I've made that list item, that first list item, wider. But here's a great example of how that affected other elements. Because I made that wider, I had to make those other items shorter, more skinny, in order to make sure there's enough space for that first list item. And this is an example of how that dirtiness caused by an invalidation can propagate. We want to be very mindful of what items we're relaying out or reformatting, that we're only doing what we expect. And you can also see how, hey, a format invalidation can cause a layout invalidation. What if my format invalidation made the font size bigger? Now I need more space and as such, I have to redo layout as well. And so that's the pattern you're going to see is that when I incur a format invalidation, I'm going to incur a layout invalidation and a similar display and composition invalidation. I'm going to go through the rest of the display pipeline to get my new content up there. And a display invalidation would be something like a color change. A composition invalidation is something like an opacity change. So as we're seeing time spent in the UI framework in a given critical path where you're not meeting your goal for the scenario, there can be two things that are contributing to that cost. One is that complexity of the UI. We talked about all the work that you're doing in the display pipeline to go from your items in your content to the screen. And then two is unnecessary invalidations, where you're unnecessarily redoing portions of the display pipeline again and again, and that can cause you to be spending more time than you want to be spending. And you can also see how the two are related. If you invalidate work, but your UI is complex, each time you have to redo some amount of work, you're spending more time doing it. And so this is going to tie into our strategy for managing these UI framework costs. And I'll touch on a couple of points here. There'll be more stuff online, and there are other talks too that cover different approaches to solving these problems. First, reducing complexity. So the number of elements that you're dealing with in your element tree, in your object model, are very proportional to the amount of work that you have to do in the display pipeline, right? And so reducing the number of elements you're dealing with, whether that's by being aware of what templates you're using, make sure that you're using every div, every block in your template, and if not, let's get rid of that so that we don't have to deal with that item. We're looking for ways to get rid of get rid of items we don't need, reduce the number of elements we're dealing with, because that means for each element we have to format, we have to lay out, we have to display, we have to compose, we have to do all that work for each element. So let's reduce the number of elements so that we have a more simple app. Text and flow considerations. This is a great example to me of how dirtiness can propagate, and where dirtiness means that, hey, I have an element that needs to be relaid out or reformatted or whatever it may be. And text and flow, consider the amount of work that the UI framework is doing on your app's behalf to get your text to the screen. If I have a block of text, the UI framework is figuring out, okay, how many characters will fit on this line of text? When do I break each line? When do I move a word over to the next line? How many lines does this paragraph need? And if I have other text underneath that paragraph that's affected by that paragraph too, it's all going to flow together. And so if I invalidate some of that work and let's say I make that first paragraph of text a little bit bigger, I have to redo that work, redo that calculation. So that's one of the things you can take into mind when you're designing your app is how many times am I changing the text size? We've seen sometimes where you can have a design where the font size is managed on a slider, and that means each time you're moving the slider a little bit, we're redoing the work to figure all of that out. If instead you have a couple of set stops in your font sizes available, we do that once because the user has decided exactly what size font they want, and then we do that calculation once, and then you're done, as opposed to doing it 10 times to get from size 4 to size 3, right? The content virtualization, you guys might already be taking advantage of this. If you're using lists, grid views, whatnot, they're probably virtualized. The reason you want virtualization of content virtualization is that it reduces the number of elements you're dealing with. So content virtualization means that, hey, I have a list of 1,000 items that I'm dealing with that I need to display to my user. I'm panning through it, and I have new stuff I want to show, right? Content virtualization, instead of dealing with the 1,000 items, will deal with a couple hundred instead. And it's going to pluck new items. As you pan, the new items that would go there, will pluck them in there, into your tree, so that you're only dealing with that couple hundred at a time. And this really allows you to reduce the complexity of your app, because each time you incur an invalidation, you don't need to redo the work for thousands of elements. You instead redo the work for hundreds of elements. Arbitrarily speaking, you can set your own controls, I believe, on how many elements you're dealing with at a time. Batching, maximizing batching. This is another great strategy to deal with excessive invalidations. Let's go back to that example of that mail app or that RSS app where you have a list item of content and you have a viewing pane that has the content for the full content for a given item, the full mail or the full RSS item. If your user is switching from one mail to another or one RSS item to another, consider the work you're doing. I have to I need to highlight the new button, the new item that's tapped, the new item that's selected. I need to erase the old content that was on my viewing pane, and I need to put the new content from this new item onto this viewing pane. Now, if I do those steps without batching, if I do them one at a time, there's going to be some invalidations incurred, right? I mean, where you first highlight the button, okay, that's fine. Now you're going to do a bunch of work, go through the display pipeline to get rid of the content that's on my viewing pane. And then I'm going to go through the display pipeline again to put new content in that same exact spot on the screen. And so that means you went one time through the display pipeline that you didn't need to. And if you're seeing delays in this scenario, if this is not as snappy and as responsive as you want it to be, then this is one of the things you can do. You can instead batch all of that work into one operation where when the user taps on that item, you go and, hey, I'm going to change the color. I'm going to highlight this list item. I'm going to pull down the old content and I'm going to put up the new content for this new item all in one go before I yield to the framework. And this time, I go through the display pipeline once. And that means, hey, I have a snappier, more responsive experience for my customer. Finally, isolating dirtiness. So we talked about dirtiness, how a dirtiness means that, hey, there's an element that needs to go through the display pipeline again. Isolating dirtiness pretty much means, hey, let's be sure that you're relaying out and displaying just what you expect. If you're seeing a ton of time, this is another place where you can look. A ton of time spent in the UI framework, excuse me. This is another place where you can look to see, hey, maybe I'm relaying out a ton of stuff unexpectedly. And we can just figure out how to isolate that dirtiness instead. Now that's fast, where we talked about those responsive scenarios, getting to that fast launch, navigation, loading content, whatnot. We talked about the critical path, UI framework, all of that. Before I move on to Fluid, does anyone have questions? I'm happy to take some time to answer some questions now. How are you guys doing? You could do a pop quiz on this. You'd be all good? Ish? All right. Yeah, this will also be on Channel 9, and we will be available to answer questions. I'll be available afterwards. Sorry. Yeah, what's up?
I was just wondering about the virtualization of the element tree. You were talking about bringing more elements in. Does it drop elements off the beginning? So is it kind of windowed? Or
Absolutely.
Is it just adding?
Yes. Yeah. We'll trim at some point. We're not super aggressive with it in that because someone may like pan this way and then pan back the other way, right? Sorry. And to repeat the question, in case people who are watching the recording didn't hear, the question was, will you trim items out of the tree or object model when you're panning? And the answer is yes, though not very aggressively. We'll keep them around for a little while so that if you pan forward and backwards, they're still there. And we'll talk a little bit more about panning when we get into the Fluid section as well. Thanks. Any other questions? Cool. Okay, let's move on to Fluid. So for Fluid, we're talking about scenarios like panning, animations, transitions. We want to make sure these scenarios are smooth, glitch-free at 60 frames per second. And glitch-free, what that means is when I'm panning, when I'm experiencing a transition or whatever it may be, that it's smooth. For example, in panning, if I see it stutter, if I see it pop, and then sort of race back up and catch up and continue, that's a glitch. We want to make sure our users don't experience any glitches, that we're at 60 frames per second. Let's take a look at an example. We'll go back to that demo app. And here I have the panning issue loaded up. And here I can see, can you guys see a couple of different things? I'll call your eye to it. The first, the most obvious is the content. We can't keep up with the panning. Why is that happening? I'm sure you guys have seen that too. And I don't know if you can see the little ripple as I was panning. That was also a glitch. Why is that happening? This is not the experience I want to ship to my customer. And so to understand what it is we need to do to get to 60 frames per second, glitch-free, and to keep up with content, the first thing we need to know is what is a VSync and what is a frame. So a VSync is the time when we throw pixels on the screen. So we talked about the display pipeline, where you're figuring out what items you're dealing with, what they look like, where they go on the screen, putting them on different layers and composing them. At the end of that process, we're throwing those pixels of what things look like on the screen into some buffer somewhere. Whenever a VSync happens, we take those pixels and we flip them to the screen. So in this graphic here, you can see over time, each of these red lines represents the point in time where I have a VSync. This means I need to get some amount of work done in time for that VSync. The frame, we're going to define a frame as what happens between two VSyncs. Okay? So in order to get that 60 frames per second experience, to get those smooth animations and transitions, we have a certain amount of work we need to complete before a given VSync. We need to be ready and have this work done before a VSync. So here we can see that we have CPU and GPU work that has to finish. And in this first frame, and I'm defining frame as the time between those two vsyncs, I'm meeting my goal. I have my CPU and GPU work done in time. Second frame, same deal. The third frame, though, I see I have extra CPU work, extra GPU work, and suddenly I'm not ready in time to meet that vsync deadline. This means I've just experienced a glitch. And this means that this frame has extended beyond these two vsyncs. This work that's happening needs to span more than one pair of vsyncs. So the work that needs to happen, when we talk about managing the amount of work that's happening in a given frame, the work that needs to happen is done by DWM, Desktop Window Manager. So this is what's doing the CPU and GPU work for every frame. And then the CPU work, that's proportional to the complexity of your UI. So how many elements you have, how many items you're dealing with. DWM, the CPU work DWM does is proportional to that. The GPU work is proportional to overdraw. So overdraw is, let's go back to that example with Photoshop. Let's say I have 3 layers, and I have a red box on the first layer, a blue box on the second layer, and a green box on the third layer at various levels of translucency. Overdraw means that, hey, they're in the same spot, and the GPU had to go and ping every pixel on each layer in order to figure everything out. Now, that's a high-level abstraction. There are, again, lots of complexities and optimizations in the platform. So I encourage you to use the tools to dig into that. But the GPU work is typically proportional to overdraw. Now, DWM, it's really good at a couple of things. And that means it's capable of meeting these vsync deadlines. It's possible to meet these deadlines with DWM. And the way we're able to meet them is because DWM is really good at display transforms and opacity. If we take a look at this figure here, we see we have body, this blue box, and list, this red box. These are 2 different layers that is handed to DWM to compose them. And it's really good at display transforms and opacity. So you can see on the right there, this might be the scenario when I tap on that panning issue page, and the list starts at the bottom, and it's very translucent, transparent. And as that animation finishes up, it takes up the whole screen, and it's fully opaque at 100% opacity. And that work is done by DWM to get that there. Sorry, you had a question? What's up? In terms of what? It's not rendering objects. Sorry, the question was, what's the story with DWM for HTML applications? The story is that DWM is still involved for both XAML and HTML, and particularly in 8.1, especially so for XAML. To answer your question about HTML, his question was about, is DWM doing the rendering of the different items? What I'm talking about here is more so that it's dealing with the different layers. It's not so much the rendering of each individual item, but once you got past that display phase of that display pipeline, display and rasterization phase of the display pipeline, DWM is doing that composition phase, where you already have the layers, it's already rendered, and now DWM is just moving them around and making them transparent or opaque. That's all DWM does. Does that answer your question? Cool. All right. Yeah, if you have a more specific one, we can follow up more too. Okay. Now, so just to make sure you guys got this, DWM is capable of doing these great smooth 60 frames per second animation and transitions, such as this example on the bottom right, where you're going from this list and making sure it's fully opaque and taking up the whole screen. And that can happen at 60 frames per second. It's capable of doing this because these transitions, animations, panning is happening independently of the UI thread. So we talked about the UI thread before, how it's key to responsiveness. And it's doing a bunch of stuff, right? It's busy doing a bunch of stuff to get your content onto the screen. DWM composition, however, can help with meeting those vsync deadlines. And those deadlines, to give you a sense of the scale of that, you have 16.7 milliseconds to get your CPU and GPU work done in time for that vsync deadline. Now, DWM is fully capable of doing that. And it's good at those opacity and display transforms. And so that's what we take advantage of to do these independent animations and independent touch. They happen on the composition thread. And all the independent animations that you use, they're only display transform and opacity dependent, right? And because of that, we can hand it off fully to DWM, and you can get 60 frames per second without being dependent on the UI thread. Right? Similarly with panning, independent touch means that touch input isn't super reliant on the UI thread. We instead process that input and pass that off back to composition to do, again, that panning. And composition is going to apply those transforms. And so we keep things free of the UI thread, and we're able to meet that 60 frames per second goal by relying on composition. So to achieve 60 frames per second, if you're seeing glitches, pops, less than 60 frames per second, not smooth experiences, what you want to look at is look at the amount of work DWM is doing. Look at the CPU and GPU work on each frame. And if you're seeing a lot of work, if you're missing those vsyncs, you need to look at simplifying your UI. Is there too much CPU work? Can we reduce the complexity of the app somehow? And that goes back to what we were talking about in FAST. If there's too much GPU work, can we reduce the amount of overdraw? And once we do that, great. Now we're at 60 frames per second. We can pan fully, and it's going to be very smooth, 60 frames per second. It's going to look really, really nice. But there is one more problem that we have to deal with, and that's render head and content virtualization. So you saw when I flipped over to the demo, as I was panning, the content can't keep up. What's happening there is, again, to go back to content virtualization, we're taking the items and we're plugging them in, and we have to go through the display pipeline for each of those new items to get them ready, right? And we're going to do that ahead of time. We see in this graphic here, I have a view, and I have my list of items, and I've only rendered a portion of them. That means I've gone through the display pipeline for a portion of them. So if I independently pan in or out, they're ready. Now I do render ahead and behind a couple of pages so that as I pan, it's possible to keep up. Now as I'm panning, as I pan faster and faster, content virtualization means I'm putting in those items into my tree and going through the display pipeline again, right? And if we see that, hey, I pan too fast, or for whatever reason, I can't keep up, I'm going to see through to black, as we saw in the demo earlier. And then if you give it a moment, it catches up and it renders back. And it keeps going. To answer the question earlier about are we trimming these items as well, for simplicity's sake, I didn't do this here. But yes, after a certain point, we do trim what we rendered and what we keep around. And we go back to having roughly 3 pages rendered ahead, 3 pages rendered behind, so you can pan fluidly and have content ready. Now, if you see this problem, where as you pan, you're seeing through to black because you can't keep up, what's happening there is that render ahead is still on the UI thread. The UI thread, again, is what's doing those framework tasks, right, to get through that display pipeline. If you're seeing that you can't keep up, that means that there's too much work for the UI thread to do as you're panning. And so we want to drill into the UI thread and see where is it spending its time. Now, alternatively to drilling into the UI thread and trying to simplify things, you can also look at multi-stage rendering and using placeholders. And there are other talks that talk in detail about that. And I'll link you to it in the resources section in a few minutes. But if you're not going to take those approaches, then you want to understand, why am I spending a lot of time in the UI thread that's preventing me from having content ready as I pan? All right, so that's fluid. This is what vSyncs frames, composition, this is what we need to know to deliver on that smooth, glitch-free 60 frames per second scenarios for panning, transitions, animations, whatnot. And to sum up, if your app is not achieving 60 frames per second, let's simplify the UI. If it's too much CPU, reduce the complexity. Too much GPU, reduce overdraw. If you can't keep up with panning, let's look at, hey, what's the UI thread doing here? So before I wrap up, do you guys have any questions on fluid? How you guys doing? Make sense? Yeah, what's up? That's a great question. The question was, why do we care about 60 frames per second instead of 30 frames per second? And if you look on a device, and if you look at a scenario and you compare between 30 frames per second without glitches and look at 60 frames per second without glitches, 60 frames per second is just so much better. And your eyes can just easily tell that. Your eye is very sensitive and can tell that 60 frames per second is more natural, more fluid. You can keep up with it. And so that's why we care. Our users can see that. And especially as as more and more apps and our start screen, that's running at 60 frames per second and all of that, we want to make sure our apps are also capable of displaying that same level of fidelity. It's not just panning, or the question was, is it mainly panning that we care about for 60 frames per second? That's the most obvious scenario, but any animation, any transition, particularly for games, we want to also be aware that, hey, can we deliver at 60 frames per second? And with 8.1, that is easier than ever. Like this demo app initially was written for 8, and it was even more obvious that you had lots of issues achieving 60 frames per second. I upgraded this to 8.1. I was like, oh, this demo is barely working now, or working. It's a lot easier to achieve 60 frames per second with 8.1. Any more questions? Yeah? Mm-hmm. The question was, how do you handle scaling across a variety of hardware for a given app, given that it may run well on my huge desktop machine or on my 8-inch tablet and not so much on other devices, depending on the hardware it's running on. And if you were at Will Sturgeon's talk earlier on planning and architecting your app, he talks a lot about that, how you have to take into mind what hardware my users are running on and then test on that hardware as well. And so that's what I'd encourage you to do. If you have a particular device that you're not meeting your goals on, hey, let's test that app and see how can we make it better there. And if you make it better there, it's going to translate to a great performance across your diverse set of hardware. So that's what I encourage. Cool. Yeah? Okay. Sorry, I couldn't quite.
It's about 60 FPS, right?
Right.
Why not 70 or 80?
It's a great question. So the question was, why 60 frames per second, but in a different way from earlier. It's more about why not 70 frames per second or 80 frames per second. And it's because of the display refresh rate of your screens that are out in market now. You probably see 60 hertz thrown around, and that's where that number is coming from, if that makes sense. At some point, if we all have 120 hertz monitors, and then maybe we have less time to complete that work, get that CPU and GPU work done. All right. Okay, I'll be around for more questions. Let me wrap up. Let's talk about the analysis approach, where we can put these ideas into practice. And then analysis approach is really an iterative one, where first you want to identify a problem. And a problem may be, hey, my launch isn't as fast as I want it to be. When I navigate to this page, there's noticeable delays. My panning isn't as fluid as I want it to be. And as you define these problems, and you see that you have these problems with your app, next you want to measure that scenario. You want to capture a trace. This screenshot is of the Windows Performance Recorder. Shel Sterioff in the next session that's starting at 5 will show you how to use the Windows Performance Recorder and the other parts of the Windows Performance Toolkit. And she'll show you how to capture a trace of the problem. Once you capture a trace, you want to analyze it. And when you're analyzing it, you want to look at, hey, what's that critical path analysis that we were talking about? What resources are you blocked on? Are you waiting on the network? Are you blocked on disk or CPU? You want to look at the UI thread. If I'm spending a lot of time in the display pipeline, that means I'm not as responsive as I can be. You want to look at what the UI thread is doing. And in general, look at, hey, where's time being spent? Am I spending a lot of time in layout? Am I spending a lot of time in formatting? Is there a lot of GPU work that's happening? Is there a lot of CPU work that's happening in the panning scenarios? And as you analyze, you'll get, given that you're the developer, you know how your app works, you'll be able to make inferences about how you can modify your app. And there's resources online with best practices and whatnot on the Dev Center, on the Performance Fundamentals section, that you can try to make things better. And that's what we encourage at this point. Use the tools, dig into what's happening in your given scenario, understand where you're spending time, and then make some changes. See how you can make your UI less complex. See what you can do, and then try again. Iterate, capture another trace. Am I meeting my goals now? In terms of those resources online, I highly, highly recommend you stay for the next hour, or it starts at 5, I believe, for the session on the Windows Performance Toolkit. That's the set of tools that's available freely to all of you. You can go download it now. And it's also available on your USB sticks that you guys got. And highly recommend you stick around, and Shell will show you how to use that and all the powerful, cool things that are going on there. Visual Studio also has a set of tools for performance analysis. You can apply some of these concepts that I'm talking about also to that. However, for the GPU fluid scenarios in particular, you are going to need the Windows Performance Toolkit. So again, I encourage you to stick around. For better panning, if you're working with XAML or HTML, you want to look at one of these two talks. Shipalo is going to talk about that multi-stage rendering for XAML, and then fast and fluid interfaces with HTML and JavaScript. That will be more on better panning with HTML apps. Finally, there have been a ton of talks, so you guys have already hopefully been to these. But if you haven't, you can catch these on Channel 9. There's talks on planning, talking about testing across a different set of hardware. That's the first talk here, planning cost less than re-architecting. From UX to APIs for 5 key scenarios, as Jason Hendrickson talks about, a couple of different scenarios like launch and whatnot, and sort of the UX design and how you want to design things to deliver a great experience there. And then finally, of course, platform fundamentals on performance. We have the XAML and the web runtime performance fundamentals, which have already occurred or is wrapping up now. And I encourage you to check that out as well if you want more information on your specific platform. And of course, there's more stuff online, and you can download the toolkit, the Windows Performance Toolkit, for free by just going to that link or just checking out your USB drive. And so with that, I'm happy to take any more questions. Do you guys have any more questions? You're all solid on this? Okay, cool. Well, I'll also be here for the rest of the time today, and then we'll also be at office hours tomorrow. Look for us in the Windows area, and just ask people about the Windows Performance Toolkit and performance, and you'll likely find us very easily. So yeah, thank you so much for listening. Appreciate you guys coming out and learning about this stuff. If you have any questions, I'll still be here. Thank you.